and I just want you to welcome you today for the third Lisbon AI Seminar. Thanks for all the people who are here in the room, and thanks for all the people online. Today we will have Mariana Seabra. She has a PhD in mechanical engineering, right? And she does a master's in philosophy, which I found perfect in the whole arrangement that we're talking in the seminar. And at the moment you are a researcher at the FLUL, right? At the what was it called exactly?
Center of Philosophy.
Center of Philosophy of the University of Lisbon. And she will talk to us today about patterns, algorithms, reflecting or shaping the world. And here we go.
Good afternoon. First of all, I'd like to thank the invitation to Klaus, Paul, and João. I'm very glad to be here. I also thank the audience and the people at home. Especially the audience, because today in Lisbon we have a wonderful beach day, so we actually make the effort to come to the university today. My talk will be about patterns and algorithms, mainly from an epistemological point of view. I'm sorry for disappointing a little bit those of you that were expecting me to talk more about representation and more metaphysical questions, but this is a big project and I start for this part. But as AI is a multidisciplinary field, I will also introduce some of common AI techniques. So the first part will relate more to my engineering background, and the second part will be more the philosophical debate. So, as you know, AI is a multidisciplinary field. It includes computer science and other branches of engineering, science, and also philosophy. Although current state of the art, AI has a very narrow concept of intelligence. In current AI systems, intelligence is defined as the ability to perceive the environment, analyze the collected data, and then react. This reaction can be something very simple as to assign a particular object to a box in a factory, or can be to help supporting decisions, for instance, stock trading, and eventually medical diagnosis and so forth. So we see that AI and computer science, they intersect many areas, and they are becoming very important in science practice. So the methods that were typically developed in computer science departments, they are now being used in chemistry, also mechanical engineering. That's where my first contact with these methods comes from. And also they have made their entrance into philosophy, especially in the 90s, as many of you know. The connectionist theories of mind were developed and caused a big fuss. Although I think to better apply these models for cognition and philosophy of mind, I think there are significant advantages to see how these methods are used in science practice. So we get more understanding on the methods, we see what we can conclude, how can we evaluate our results, and from then I think having a more solid understanding from what's happening in the sciences, then we can save the lessons and apply them in the philosophy of mind. So I will be, this presentation, I'll just focus on the first point. And although I have some ideas in this more philosophy of mind field, and if you wish, you can ask me during the Q&A. As a departure, computation is already very common in the sciences. There has been some debate whether it constitutes or not a novel scientific method. And I think the current analysis, most people agree that computation presents something new besides theory development and experimentation. But so far, until probably 10-15 years, most of the computation in the sciences was done in the physics-driven sense. And by physics-driven, I don't mean exclusively science is related to physics, but it can also be in chemistry, eventually biology, any field where we can have governing equations for the phenomenon of interest. So typically, physics-driven computation had the goal of solving differential equations. And for that, we needed to supplement those equations with something more, typically boundary or initial conditions, and then do some discretization and have some numerical implementation. A typical example of physics-driven computation is the finite element method that is used nowadays very much in the industry, for instance, to assess safety of structures and do building and mechanical parts projects. But in the last years, we have an increase, a huge increase of data-driven methods. This type of methods differ because the departure information usually is very minimal. We have there is a property that we want to analyze in the population. For instance, we want to analyze the propensity of a certain. So we collect the data and that we apply a certain mathematical template. In these data-driven methods, one of the biggest differences is that often we don't need to know the governing equations of the phenomenon. And that's one of the reasons that makes
Can I ask you something? But do you believe that these, let's say, two things can be split?
No, they are also hybrid methods.
Okay.
And this is to create a kind of departure division, so to facilitate our analysis of these methods. And nowadays we have often hybrid methods. For instance, we need to calibrate some material parameters that we want to use in the differential equation, so we can use like that database analysis to find the parameters for instance, a material that has not been experimentally characterized, and then infuse that in the physics-driven model. And also backwards, we can also compare. But to make things more clearly, I have here one example. We have the Lorentz system, which is a system of differential equations often used to study the atmospheric movements. And typically, the Lorentz system of equations would be numerically solved, for instance, using there's an area which of the methods. And we would have to go to this cumbersome process to discretize the equations and apply some numerical methods. So on this picture here, I have a comparison between what I call kind of more traditional computation and the prediction of the system's behavior using a neural network. In this case, a very simple neural network, only with 3 layers and 10 nodes of each layer, was able to learn the dynamics of the system to a database of 100 different initial conditions, and it's able to represent and predict the solution pretty well. The difference here is, to obtain the neural network solution, I don't need to know almost nothing about the system. I just need to collect data on the different positions of the system for each time. So we have seen an explosion of the use of methods such as neural networks to learn patterns from data. And used in very different ways. Neural networks also nowadays have a huge diversity. They are far from the original neural network that create a big fuss in the philosophy of mind, which is more like the first type, that we have some input nodes, given nodes, and then output nodes with some more or less simple activation functions. And nowadays, for instance, convolutional neural networks have become very popular. Convolution is an operation that, for those of you familiar with Fourier series and Fourier transform, the convolution in neural networks works a little bit like the Garvor Fourier transform, that we can kind of integrate parts of our data, and for instance, increase some special features of interest. If we have an image, we can tune our model to augment certain frequencies, for instance, so we can see the edges, if we can see special shapes or colors. So nowadays, there has been a proliferation of this kind of methods. And as these methods grow complex, they kind of create the question, how can we trust the results that we obtain for such complex algorithms? Yes. Another family of data-driven methods are the so-called matrix decomposition methods. One of them is the dynamic mode decomposition. This method works, it's not the same, but it's a little, we can draw a parallel between Fourier series and this type of method. So basically, this method extracts the fundamental modes of the dynamics. Using simply matrix decomposition, we need to collect snapshots of the system for certain intervals of time, and we approximate the nonlinear dynamics of the system of interest by a linear dynamics. So if we collect the snapshots in intervals sufficiently small, it will be reasonable to say that the nonlinear system that I had in the beginning can be approximated by a linear system. So we construct this A matrix that is just the matrix that interpolates from instant t to the instant t plus 1. So this is also another family of methods with great potentiality, and this also falls in the category of equation-free methods. That is, I don't need to make any explicit reference to natural laws to use these methods and have good predictions. And we can go even one step further. These methods can be combined to the search for partial differential equations. So I can have a system of interest. I just have data sets of the dynamics of the system, and I can decompose the modes and then search which partial differential equation system would match those modes. And one of the examples is this in the algorithm by Brunton and Rudy. So in this example, they analyze a turbulent flow and they retrieve the Navier-Stokes equation. They have a very interesting paper where they recover several classical PDEs, such as Schrödinger equation, Navier-Stokes, and some others. So faced with this diversity, and I just mentioned like 2 families of methods, and we have a lot more like clustering methods, most typical used from statistical analysis like PCA, BOD, etc. So we foresee that there are usually 3 typical goals from which this type of algorithms are used, namely classification, when we want to fit the data into classes, a regression of data fits, For instance, I want to develop new steel alloys. I have chemical compositions and mechanical properties. And from the data, I want to predict the mechanical properties for a new composition. That would be an example of regression, and also the analysis of dynamical systems. It's very hard to classify the types of algorithms. We have a matrix decomposition family, statistical inference, and machine learning. But statistical inference and machine learning, they are not different types of algorithms. They are just two perspectives for looking at an algorithm. So usually people that work more towards statistical inference, they want to analyze the type of reasoning that the algorithm is performing. That is, when we use these methods, we are trying to reasoning from incomplete information. So if we had the complete information, we could do deductive reasoning, but here the information is incomplete, so we have to find strategies to evaluate if our reasoning is good or not. And the machine learning community, they share the same algorithms, but the machine learning community is usually more interested in performance and accuracy of prediction. So these are not exactly different types per se, but different ways to look at the same thing. So first with all this, and also from the classical computation point of view, all these computational methods pose some philosophical questions, namely at the level of the metaphysics. So this type of patterns that we extract in the equation tree methods, can we extract some ontology? Do these patterns have any meaning in the world? And this kind of inspires a bit the title of the presentation. And then we also have an epistemology part. And basically, from now on, I'll try to answer the two highlight questions, namely, do data-driven methods possess any degree of epistemic capacity? And if so, are they more or less epistemically opaque than the physics-driven methods? Of course, the two parts of the project overlap, and this is a very recent project, so I'll now try to talk about how, which stage have I gone through. Just as a preliminary, in the philosophical debate, computational science is defined as the development, exploration, and implementation of computational models of non-mathematical systems using concrete computational devices. This definition doesn't mean to be exhaustive. It's just a kind of working definition that tries to embrace the whole diversity of computational methods available. And also another important preliminary is that when studying computational science, the typical units of measure for science, they don't apply, namely the paradigm and the theory. Why? Because these computational methods, they are applied in a wide range of different subject matters. So the same neural network can be used to solve a biology problem or mechanical engineering problem. So we have to find here new units of measure. And I decided to use the framework defined by Humphreys, in which we have a template and a model. So the template is basically just the raw mathematical form. It can be a differential equation. For instance, here in the picture, we have some different differential equations, but we can see that the formalism of the equation is the same across subject matters. So the idea of the template is to extract this raw mathematical formulas, and then the template will have to be supplemented with something else to create a model. So in the case of differential equations, we'll have to supplement it with initially and boundary conditions. We need a justification for adoption of the template. In the case, for instance, of a data-driven model, we will have to supplement it with a data set, and also to have a justification for appliance for application. For instance, this template can also be typical statistical distributions. So often when we want to use, for instance, Poisson distribution or a Gaussian, that will be the raw template. And then I want to apply that statistical distribution to a problem of my interest. I need to supplement it with something else to create the model. And now let's see how having this framework of template model as a background, how can we deal with epistemic capacity when using computational methods? There are a few definitions of opacity in the literature. The definition that I find the better departing point has been given by Humphreys, which says that process is epistemically opaque related to a committed agent X at time t, just in case X does not know at t all of the epistemically relevant elements of the process. Nevertheless, this definition had many critics. On a paper 2015, Newman says that computational processes are not opaque if one respects the basic rules of software engineering. And I will argue further that some types of opacity can be overcome by a proper software construction, like to organize and commented codes, but not all types of opacity can be overcome in this way. Weisbart criticized Humphrey's definition mainly for being too narrow, because he argues that Humphreys only considers a computational layer. And he proposes a dispositional definition. Although my main point here will be to defend Humphreys. Finally, on another paper, San Pedro says that Humphreys' definition opened the ways for a graded notion of opacity rather than an all or nothing. Until San Pedro, the debate was focusing only in having all or nothing accounts of the epistemic opacity. So the plan for now on is basically to defend Humphreys and by interpreting his definition and highlighting the advantage of keeping it a subject-centered definition. And if we have time, I'll show some strategies to overcome the opacity. In this debate, opacity and transparency are seen as opposite sides. So that is, if a process is totally transparent, it is not opaque, and reversely, if a process is completely opaque, it lacks transparency, and we have many gradings in between. In my understanding, we could have opacity in a dispositional sense that say this particular method is opaque or not. Although I think that taking the subject out is not a good thing, because it prevents us from drawing the normative consequences that we should take from the definition. That is, I prefer to look at the opacity transparency question as a glass that is dirty and we can clean at least some of the dirt. And I will, at the final stage of the presentation, show that for many science applications, we don't need full transparency. So what we want a definition of transparency to do for us? Usually when we say that a process is opaque or not, we want to have a hint on these questions or questions related to this type. That is, can I trust the results? How does the model parameters impact my final results? For instance, how does the initial conditions impact my results? Or also I can have doubts on how the parameters of the template impact my results. For instance, I want to know how the number of nodes or layers can impact my final results. Or in a physics-driven example, I may want to know how my time discretization interval is affecting my results, just to give quick examples. Also, it would be good to have an account for both physics-driven and data-driven, because as we talked in the beginning, often the strategies are hybrid. So it's good to have both covered by the same definition. It's also good to have degrees, because not always the same degree of transparency will be required. And finally, epistemic peers should look at the method with the same level of transparency. So here we have advantages in keeping a subject-related definition. In the literature, there have also been proposed different types of opacity. I don't have much time, so I'll skip a little bit this. But my strategy here is to say, instead of different types of opacity, what people are really talking about are the different epistemically relevant elements. And in terms of computation, also looking at Humphrey's work, although Humphrey's in his examples, he just mentioned more computational layer related examples, and he talks a lot about surveillability, about an agent be able to check every step of the computation. I don't think an agent necessarily has to check all the steps of the computation for the process to be transparent. For instance, I can just solve a simple 1D differential equation for a heat bar. Very simple example. I can have a finite differences with 1 million intervals, and I don't need to check what is happened for all computation from time t0 till time 1 million, because I understand perfectly how the algorithm has been constructed. So total surveillability may not be required. So I think there are three main types of epistemically relevant elements, and they can be hardware related, template related, and model related. So in fact, although Humphreys never took his definition to be applied in this way, I think he provides in his theory all the tools so we can give a new understanding to his definition. So my proposal is to say that a computational process is fully transparent if and only if X knows and understands all the epistemically relevant elements of the process, namely all the elements at the level of the hardware, template, and model of Y. And why are these the important elements? A hardware level, it's certainly where things often can be tricky, because there's a kind of physical implementation of the computer. We don't know how the electrons are moving inside the computer. But for most science projects, the hardware level is not very important, because these algorithms are written in high-level languages. So at most, the hardware will impact in the machine precision, but when we apply these methods in applied science from physics, biology, etc., the error that we will have in our models will always be much bigger than the machine precision. So except if our project is really... What? It's really directed to the hardware. Sorry, I was saying that in many of the science problems, the hardware will not be the relevant thing to check for. As long as we are right that the hardware is functioning well, we can move to the template and the model level. At the template level, we have things like the algorithm, how the algorithm is instantiated in code, and we can have several template parameters like time discretization, if I'm discretizing my equations in an implicit or explicit way, and number of layers and nodes in a neural network, number of truncation modes in the dynamic code decomposition, and so forth. Finally, at the model level, we will have the integration between both things, like the raw algorithm and then its application. And here, we often need infusion of expert level. So when we want the required transparency, we may need to act in these three different levels. Just to finalize quickly, full transparency is not always required. For instance, if I just want to perform a regression task, often is enough to know that I'm in an optimal fitting region. So if I do regression with a neural network, I don't need to inspect if the neural network is being trained and instantiating different patterns within the training, etc. I just need to make sure that my error is bound. So in this case, if I just want to perform a regression, my level of transparency will be much less than, for instance, if I want to use a neural network model to study visual perception. In this case, it will be necessary to inspect what is happening inside the network. And just to finalize, there are several techniques that can be used to increase transparency at each one of the levels, and it will be a project choice to see the required level of transparency and then the associated techniques. In conclusion, we can say that computational methods have three types of epistemically relevant processes, namely at the hardware level, template level, and model level. Full transparency is not always required for a particular science project, and there are some techniques that can be used to relieve opacity. Of course, to fully evaluate the model transparency, we need the second part of the project because we will need to define a certain ontology between the patterns we are analyzing and what we are processing and how does our model maps the real world. But that will be the second part of the project. So I thank you all for your attention.